Greetings, my name is Ogan Gorel, and it is my honor and pleasure to present to you on the future of medicine, specifically an area of bioelectromagnetics called protein electrodynamics in terahertz medicine. I actually have a history back in Grenoble. I worked there in the summer of 1987 and several years after that in collaboration at the Institut Lau-Langevin, which many of you are very familiar with. So I have a special fondness for that beautiful area. This is my original appointment letter, and this is a picture of me there with one of my colleagues. And we published a paper with the principal investigator Giuseppe Zacchi on the tertiary structure of bacteriorhodopsin. And this is a short excerpt from a book that I've published since then, describing the magical journey into the Alps to Grenoble from Geneva by the train.
A tune flitted in my mind. I hummed the Tristesse, Chopin's lyrical etude, lilting in synchrony with the train as it meandered past quiet pastures, clinging alongside glistening lakes, glittering the lush, secretive valleys. Up toward the Alps we resolutely advanced. At times the soft clacking on rails, pacing this wistful journey, would slow. Pausing to contemplate, it might seem, God's verdant creation. The music sounded hymnal homage to deeds past, and of a certain hoping too, a melding of traditions melting, possibilities crystallizing. I imagined Gounod's nervous waltz from Faust et Marguerite, couples dancing in magical alpine castles, gaily unaware of a world of elegance and false forethought to be blasted forever by the Great War. What lay ahead? Soaring with the music then, rising to meet the French range, I dreamt that amongst this glorious geology I might find beauty, nature, history redolent, and future resplendent.
So I begin this webinar with two quote from the famous German philosopher Immanuel Kant. Two things fill the mind with ever new and increasing admiration and awe: the starry heavens above and the moral law within. So this seminar will take 4 parts. I'll talk about some key questions, fundamentals, some research results, and finally some applications and implications. So there are 4 key questions. One is, what is the future of diagnosis? And this is a timeline of imaging with the modalities X-rays, ultrasound, PET, MRI, CT. The basic point is that no new modality since 1985. Innovation has effectively stalled, with most of it being incremental since then. What is the future of therapy? This is another chart of new drugs per dollars, research dollars, and you can see over the past half century that has been steadily declining. Less drugs, more money. And in fact, since the turn of the century, it costs about $1 billion to develop one drug. So apart from incremental advances, innovation has also stalled in pharma. So we need new approaches. What is the future of technology? Well, we have many techniques to predict the future of technologies. One of them is called TRIZ, based on natural evolutionary patterns, for example, landlines to wireless and so forth. So if we look at a steering wheel, rigid steering wheels progress to electrical steering ultimately. If we look at doors, a single leaf door will progress ultimately to an electrical light lock. And the same can be said for medicine. For several millennia, we've had a matter-on-matter paradigm where a drug physically binds to a protein, and likewise in surgery, a device physically interacts with the target tissues. So the future must be some form of energy on matter paradigm, and the question then is what energies and when will this happen, and we'll look into that in this webinar. The last question, more theoretical, is how does life work? This is the yeast proteome. Those proteins are the nodes, and the lines are the interactions between those proteins, hence the interactome. It looks like a big mess. How do these proteins find each other in this random mess, and the miracle of life occurs? So where do we go from here? What will be the future of medicine and healthcare? How can we better understand the fundamental mechanisms of life? So the story begins over 30 years ago, before I went to the ILL. I worked in my senior thesis with Martin Karplus at Harvard, and I remember when I first met with him in his office, he told me that proteins are neither solids nor liquids. They are something in between, and that was very fascinating and very compelling to me. So second part is some fundamentals. Proteins, what do they look like? They are, of course, the machinery of life. They are the target of drugs, and here are 2 examples: myoglobin, mostly alpha helical, and basic fibroblast growth factor, mostly beta strand. and two other examples, the androgen receptor and human growth hormone. And the bottom line is that these proteins come in many different shapes and sizes. And what do? They basically do most everything required by life. They are structural proteins, storage proteins, transport proteins, hormones, receptor proteins, contractile proteins such as in the muscles, defensive proteins like antibodies, and of course enzymes that catalyze reactions. And here's one example of the voltage-dependent potassium channel that is a key element of the nerve signal. And in response to a voltage, in response to an electrical change around it, it will have this big change in its structure, opening up the channel to allow potassium to enter into it. So what are the axioms of protein electrodynamics? There are 5 of them. One of them is that proteins vibrate. Number 2 is that proteins are charged. This is another protein involved in muscle nerve function, acetylcholinesterase. It has a negatively charged reddish pocket here and positively charged bluish around it. Third, of course, is Maxwell's equations, which dictate that vibrating or accelerating charges will emit and absorb electromagnetic radiation, and therefore proteins will emit radiation and proteins will absorb radiation. And these are the 5 axioms, or facts, if you will, of protein electrodynamics. So looking at this in a little more detail, Martin Karplus and others taught us that proteins vibrate, hence protein dynamics, and this is the original 1977 article in Nature, and then he, as many of you know, earned the Nobel Prize in 2013 for chemistry. And here's an example of a protein dynamics, glucosamine 6-phosphate deaminase. And you can see the small-scale motions as well as the large-scale motions. And how do we know? Well, there are several experimental techniques for this, inelastic neutron scattering, done at the ILL in the Institut La Langevin. And this is an important paper published in Science by Giuseppe Zacchi. And it shows the force constants for the softness of these proteins, ranging between 0.3 newtons per meter to 2 newtons per meter. And what are the frequencies? Again, another neutron scattering experiment done by Jeremy Smith when he was at the ILL and Martin Karplus in collaboration, combining the theoretical predictions combined with the experimental observations for myoglobin, and they correspond to around 0.45 to 0.6 terahertz in the sub-terahertz range. So some scientific questions are essentially raised. Do different proteins vibrate at different frequencies? The answer is yes. Can we identify different proteins based on the spectrum? The answer is also yes, but not so easy. And these questions underlie diagnosis. And harmonicity of protein motions. How significant is this? This may depend. Can one influence protein function by modulating their vibrations? This is unknown, but there are indications that we can. And how far might these fields propagate? And could protein electrodynamics mediate specific interactive forces between proteins, and hence could they in effect communicate? And the answers to these questions underlie treatment. So what is terahertz? Most of you are familiar with. It is the electromagnetic energies between the microwave on the low frequency side and the infrared on the high frequency side. And it's often termed the terahertz gap at 10 to 12 hertz. That's because until recently it's been very difficult to engineer terahertz radiation. It lies directly between the electronics regime, which basically manipulates unbound or conducting band electrons, and the photonics regime, which manipulates bound or valence band electrons. But terahertz is all around us, emitted by all living organisms, as we've all composed of proteins, and in fact it's also absorbed by water. And terahertz is indeed the last frontier in the electromagnetic spectrum. This is frequency centered on 1 terahertz on the horizontal axis, power on the vertical axis, and you can see the photonics regime here and the electronics regime and the lower power that ensues when you move from those instrumentation to the terahertz region. So what are the natural sources of terahertz radiation? You remember that quote from Immanuel Kant, the starry heavens above and the moral law within. Well, the starry heavens above, to me, signify the cosmic microwave background. That radiation that's the residua of the Big Bang, the original Big Bang. It's peaked in the microwave, but actually has a terahertz tail. And likewise, the moral law within is suggestive of the fact that life itself is a source of terahertz radiation. And the New York City Police Department uses this for weapons detection. So they have a T-ray machine, and the gun, as you know, is composed of, or a knife, concealed weapon is made of metal, and it won't be emitting the terahertz, whereas the body is composed of proteins, and by virtue of the contrast can detect the weapon. And of course, it's the same principle used in millimeter wave scanners, which are slightly lower in frequency. So there are two technical challenges. One is the production of terahertz sources of sufficient power and spectral resolution, and the second challenge is that of water absorption, which is both an opportunity and challenge. So the principles of the application to terahertz medicine involve the diagnostic side, both imaging, so we can see structural elements, perhaps leveraging the water contrast, and spectroscopic or functional elements, focusing on specific proteins. And the concept of therapy being energy-based protein-specific, with three principles, that of resonance, localization, and functional modulation of the protein, either activating it or inhibiting it. And as Albert Einstein famously said, the future medicine will be the medicine of frequencies. So a few research results. Now, many of this was done when I was at site, but also afterwards at the Samsung Advanced Institute of Technology and in collaboration with other academic institutions worldwide. So one study we did was on myoglobin and hemoglobin, a time domain spectroscopy, actually three proteins, bovine or cow hemoglobin, myoglobin in green, and human hemoglobin in blue. And some features of the spectra are evident. One is there's a difference between myoglobin and hemoglobin, with myoglobin absorbing at a higher frequency, and a species specificity, or a difference between the hemoglobins of cow and humans. And then finally, a kind of emission or Stokes shift or negative absorption, suggesting that the protein is soaking up energy at the high frequencies and spitting it out at the low frequencies. And if we compare these results with those original myoglobin results, we see this peak around 450 gigahertz. Again, suggesting, it's not exactly aligned, but suggesting the importance of the sub-terahertz range for biomedical applications. So in conclusion, broad yet specific low-frequency absorption in the sub-terahertz range. Species differences are discernible. The overall fold shows similar features, and there's a possible stimulated emission with proteins at terahertz emitters at the low frequencies. Now, lest you think this is just very broad and very indistinguishable spectra, sharp protein resonances exist. This is Andrea Merkels's work out of the University of Buffalo with lysozyme and showing a 1.5 terahertz sharp resonance. And this lysozyme also changes its motion with different functions. So in the normal case, it has a hinging motion with the transition dipole oriented in this way. And in the presence of an inhibitor, it undergoes a twisting motion or twisting vibrational dynamics with the transition dipole shifted accordingly. And proteins also emit terahertz. Bacteriorhodopsin, the protein that I worked on when I was at the Institut Langevin, emits at 0.9 terahertz. And these proteins are also involved in function. And another study by Martin Karplus looking at what's called the SARC protein. SARC is a oncoprotein, a protein that's very important in many cancers. In the normal case, it does normal growth. In the mutated case, the protein allows uncontrolled growth or cancer. And this red is a heat map of the motion, and you can see that cancer proteins are different than the normal variants of those proteins. So again, when I was at Samsung, we had the Global Research Outreach or Open Innovation Program, and we looked at real-time terahertz imaging for cancer. On the diagnostic side, we did 2D spectroscopy to try to tease out these peaks. We did an experiment with the University of Southampton for the protein modulation, and then finally developing a terahertz integrated source and sensor at the UC Irvine. So on the imaging side, we did cancer with Ohio State. As I mentioned, this is the optical image, this is the terahertz image. To make a long story short, we saw differences between the normal and cancer tissue, perhaps attributable to this difference in water content and other structure, large-scale structure in the tissues. We did a similar study with Alzheimer's disease, and after many calculations, also observed differences between Alzheimer's disease samples and control samples. And in order to identify different proteins and distinguish the spectra, we developed a project with Keith Nelson and his team at the MIT for 2D terahertz spectroscopy, and had a patent, U.S. patent granted for that, in fact. So your area is very keenly interested in the semiconductors, and we had two projects actually, one with UC Irvine, as I mentioned, producing a 300 gigahertz integrated terahertz source and sensor with Payam Haidari, and then also at the University of Texas, not technically out of sight, but another research group at Samsung, also with a terahertz system on a chip. And so the concept is, with this miniaturization and low cost, we could create a handheld diagnostic device or even therapeutic device. So the overall conclusions from this research is that definite signals are observed with proteins, particularly in the sub-terahertz range, and continuous wave tunable spectroscopy may be better able. Different tissues can be distinguished, normal and pathologic, with applications demonstrated in cancer and Alzheimer's. The imaging and the spectroscopy are promising applications, and on the technology side, in particular, high power, continuous wave is very important, particularly in the sub-terahertz range, and miniaturization via silicon-based CMOS platforms is encouraging. So focusing on this intersection of biology and the physics and the engineering, as I mentioned, there are both the electronics approaches and the photonics approaches. The photonics are typically higher frequencies, and of course the electronics are lower frequencies. And given that the sub-terahertz is probably more important, it gives precedence to the electronics. And given that continuous wave specific frequencies are more important, this means that the most promising technology for the biomedical application of terahertz medicine is on the solid state side. That's my opinion. So let's go into some applications. So we fundamentally need new approaches to diagnosis and treatment. You saw this, no new modalities in imaging since 1985. Biopharma innovation stalling, and technology is naturally evolving. We will have an energy on matter paradigm in the future, and this will offer greater specificity, more non-invasive, greater effectiveness, lower cost, more rapid therapy development, and a convergence of medicine and surgery. And this is not just fantasy. This is becoming more and more mainstream. Time magazine had an article, Why It's Time to Take Electrified Medicine Seriously. Google is collaborating with GlaxoSmithKline and creating Galvani Bioelectronics and other spin-offs to build up the area of bioelectromagnetic medicine, and there are research groups growing around the world. What are the potential applications? Well, we can have an electromagnetic anti-cancer agent. We can have antibiotic-resistant antibiotics, so that the next pandemic we can potentially have, which may be a bacterial pandemic, we can quickly adjust our therapies to accommodate for that resistance. Neurological applications, diabetes, wound healing, essentially a platform technology. All of you are familiar with the handheld thermal scanner. Imagine a handheld COVID scanner. And that's indeed a project that we've initiated with Middle Eastern Technical University for a surface plasma on chip that can detect biological samples, specifically proteins, with terahertz, leveraging this particular behavior. So terahertz physics has been a challenge, but why now? There's been a growing interest, increasing patents, articles, growing terahertz market, becoming mainstream, better performance, and of course miniaturization, and most importantly, decreasing cost of the systems, particularly with these semiconductor-based approaches. And as I mentioned, Star Trek has been a pace setter in technology, the communicator, predicting the mobile phone, and of course the tricorder, potentially predicting even the quadcorder, which can have therapeutic aspects. I've been contributing to this field, as you know, academically and with collaborations and so forth, but also wrote a novel, which I quoted to you earlier, called Waves, which explores the wider dimensions of this technology, from the ethical dimension, the social dimension, adoption, and so forth, available on Amazon. And so this is chapter 23. It's not autobiographical, but it's set at the Institute, and it describes the initial coming of the idea. The subtitle of the chapter is Descartes. For several months I worked at the Institute, and this, my friend, is when I came upon the novum. The novum is the name of the idea. And as I thought, an idea, a most unusual idea, inserted itself. If proteins vibrate, as they are well known to do, and being composed of charges, as they are well known to be, then surely they would create electromagnetic waves, as moving charges are well known to do. Then, as is well known, if these electromagnetic waves were, as is also well known, to travel through space, they could impinge upon, scatter among other collections of charges, namely other proteins, and then influence them, as electromagnetic waves are well known to do. You can recognize the influence of Descartes in this logic. So I will close with some thoughts. Again, a summary. Protein molecules are the machinery of life, the targets of most drugs. They are not solid, but they are vibrating. We call this protein dynamics. Proteins have charges, positive, negative, so therefore proteins can emit energy and can absorb energy. And so proteins are like radios, which can be detected and modulated. We call this protein electrodynamics, giving rise to an entirely new approach of diagnosis and therapy. We call this terahertz medicine, the key precepts I've described in this book, Waves. So I presented around the world, in the Americas, in Europe, in Australia, and of course in Asia. And it's a special pleasure, especially with my connection to Grenoble, to present here today. I will end with a quote from Richard Feynman, one of my heroes. Everything that living things do can be understood in terms of the jigglings and wigglings of atoms. I presented at Martin Karplus' Nobel Prize Celebration Symposium along with other of his former students. And I asked them, what do you suggest after I presented this work? He said, I would do the experiment on an enzyme. If it works, it would be significant. And in the beginning, as you know, technology is not always pretty. This is the Wright brothers, of course, the first flight. And dreams can fly, and we can make a lot of progress. Of course, moonshots can become reality, and Mars shots too. So merci beaucoup, thank you, and as we say in Korea, kamsahamnida. I'm happy to engage in answering questions. You can connect with me on LinkedIn or, of course, by email as well. Thank you very much, and please take care.